Okay, we'll start. So these webinars Intellex have been conducting every week this month. This is as part of launching the new batch, and these webinars are focused on specific experience we had and hope that some of the tips coming out of this webinar would help you. So today I'm going to talk about asset inspection. It's what happens when it is complemented with some reliability techniques. So hope everyone can see my screen.
Yes, sir.
OK, thanks. So those who don't know me, I'm Rishi Marathu. I'm qualified in MSc Risk and Reliability from Loughborough University, UK. Then I'm also a Bachelor of Mechanical Engineering. 22 years I've been in this profession in railway ramps in UK, Middle East, India and North American Railways. I'm a faculty member in Intellect Services training courses as well. So today I'm going to talk about the agenda for today is how the process of signaling asset inspection is undertaken usually. And if you want to use reliability techniques specifically, I meant life cycle distributions, which is like Weibull, and there are ProAMs, are these kind of distributions. What are the prerequisites when you can use it? And we use this in a recent project when I performed the signaling asset inspection, a ProAMs life cycle distribution. We give a technique overview and an example of calculation, and we go to the conclusion. We also take the opportunity to give a short introduction of the Intellex training courses as well. OK. The signaling asset inspection, the methodology, normally it is followed is visual inspection and functional test. Nowhere I'm proposing that to replace that with a reliability analysis or anything, because the existing methods of the visual inspection and functional test adds their value. It's only about complementing this with further analysis of the failure data. So if it's a mechanical assets, there are the usual checks like wear and tear of any moving components, because mechanical elements can wear and tear over a period of time, and it can be visually noticed as well. Then you do a functional test, and if you hear an abnormal noise, if you have an experience with that equipment, you can recognize that, yeah, it is something abnormal. You need to address it quickly. And obviously, physical damage cannot be detected through reliability analysis. You have to look for it. Then you can look for the dust and water ingress, which can cause long-term damages. So those kind of things you can look at. This is not a definitive list. These are just examples to get a feel what the inspection would look for. Then electrical assets. Yeah, you will look for cable degradation, insulation damage, any kind of motor physical damage is there, and the same type of issues like abnormal noise, temperature. When it is operating, it is temperature high. You may also look at the current consumption, and if it's a point machine or say in the moving, whether the timing is within normal windows. For the electronic assets, yeah, obviously physical damage, which can be which is one of the essential things you will look for, and the wiring degradation in the boards and all that gives you a telltale sign for any kind of asset degradation, and you may want to look for replacement. Then fault indications. Every time all the faults are not relayed to the control center, so people may not know. So you look at the cards, and most of the modern cards, they have the fault indicators on it itself, so you can straight away see this component is faulty. Then you look at the environmental condition like the HVAC and the temperature inside, so that it can perform reliably. So these are normally the checks, but there could be more also depending upon the experience of the inspector. There are more checks also. In this instance, when they're obviously to get the access, we need to identify these are the equipment I want to check, and you need to inform them in advance. And because the maintenance is handled by a subcontractor, they were a bit nervous about the inspection. So all the equipment were overhauled and kept ready for inspection. So everything was working perfect. That is the issue with the visual inspection. Though many of the physical damage and other things they can't hide, but then the abnormal noise, any kind of functional issues, they can mask it for a time being with that timely overhauling at that time. So this is where we have the advantage of using the reliability techniques. So now I'll take you to one of the reliability fundamental, which is the bathtub curve. This is the first thing you would learn when you are learning about RAM engineering. The bathtub curve is a distribution of the failure rate against the operating time. And during the early part, you have the infant mortality. So you have a lot of installation issues, manufacturing defects, software issues, or systematic failures. All these kind of things would happen during the infant mortality period, which is I'll come to the beta in a minute. So this phase, because of these issues, the manufacturers give a warranty and they take that hit themselves. So they will root cause analyze each of these issues and make sure that the reliability grows and the failure rate hits the steady state. So this part is normally covered in the warranty period, and you should have a proper fracas process to support this to achieve this. Otherwise, it can go like this till the end, and after that it wears out. Sorry. And then you hit the normal life, and here the handover happens to the infrastructure operator, railway operator. So they maintain it. So this is very predictable. This should be, if there is no systematic failures. This distribution is normally called exponential distribution, where the failure rate is constant. The normal RAM equations, what we use, like the MTBF is equal to operating hours divided by number of failures. These would apply only during this normal life period. Yeah. Then after the normal life ends, I mean, probably 20, 25 years, that's the kind of a period. Yeah, maybe Ismail, you want to hide your video for the time being. So when you have a question, you can ask with the video on. Yeah, camera off, that'll be good. OK, so when it goes to the end of wear out period, so then the failure rate starts to increase, and this is the time you would like to look for upgrades. So this is the general principle of the bathtub curve. Now, the life cycle assessment, there is a shape factor called beta. This comes from the Bible or in CROAMSA, you have the shape factor. And this beta value is less than 1. That means that the reliability is still growing. You got some process in place which is helping to improve the reliability. Then when the beta value is approximately around 1, that means that, yeah, there's nothing to worry about. It is the steady state failure rate. So it progresses steadily. You plan with your spares, and also only thing you need to watch out is the obsolescence. Basically, that's not covering it. The obsolescence is that something they stop producing, you need to go for a upgrade. Then end of life, that means that the beta increases. That means that the mean time between failures increases quite in an increased rate. So after some point, maintenance is not sustainable. You'll be spending a lot of money. So it'd be better to go for a replacement. So this is the asset condition assessment. So we focus the analysis to estimate this beta estimate the beta and derive conclusions from it. So which life cycle distribution we can use. We considered two. Viable distribution. The advantage is that it is in. There are several tools available. It's also in the isograph. There is a good application which viable distribution. We can use it. Models the time to failure. There are several things when you can put also failure dates and all. Then it can be used. Then there is another distribution called CRO-AMSA. It's a very flexible distribution and it's a bit macro level compared to viable. Viable is suitable if there are some preconditions. There has to be good quality of failure data. You should have the failure data right from the inception. If you have only for the last few years, that's no good, because last few years it is worse. Then it will give you wrong results. Then viable is model time to fail. So it is meant for non-repairable systems. Suppose you got a population of assets installed. For example, relays and all, and after that failure, you're not going to repair it. You just replace it and put the new one. So when you want to use, you can do it for a population of relays, and then the majority of them start failing frequently. That means that shape factor is bad. Then you go for the whole replacement. So that's the kind of analysis you would do. CRO-AMSA is used if you have the quality of failure is not good, and we have data available only for discrete intervals. Suppose you have only 3 years worth of data, which is usable, then viable you cannot use, but CRO-AMSA you can still derive and get some good accurate conclusions. And we can model for multiple failure modes for the same component. You can have different failure modes, so it doesn't really matter. So it still give you the wear out of the assets, the condition. So in this case study, the data quality was generally not good. That is the first issue with some of the railways, especially the old railway. If you don't collect the failure data, you have no chance to improve. There is some reasonable data for last 3 years, so that we collected from 2019 to 21. So then we decided, OK, we use CRO-AMSA model is suitable for this analysis. So what are the prerequisites for using this distribution? First thing is that you should understand the failure mode. So that means that to which line replaceable unit that failure is attributed, that information should be available. And the failure mode information, you should have sufficient information to understand the failure mode, whether it's a software failure or a hardware failure and what has been done. Some data should be there. And the third important point is that you should have at least 20 failure points for the LRU under consideration. So if you don't have that much data, it is not statistically significant. Then if you're in 3 years, you don't have 20 failures, that means that you don't need to consider about replacing or anything. You can just do your normal FMEC and all. For us, that should be fine. And the failure data, when you analyze, it has to pass the fitness of good test. You can use chi-square test, and there's a 20% interval test. I will tell you in a minute when we come to that model. So these are the prerequisites where you can derive some conclusion from the result. So about the case study. This is a national railway in one of the Middle East countries. Obviously, due to confidentiality issues, I cannot reveal which project, and it doesn't really matter because we are focusing on the technique we use. And it's a desert condition. That is important to understand about why the asset inspection is being done and all. So what are the signaling assets? It's mainly the wayside signals. And you have the axle counters for train detection. You got interlocking. It's a conventional signaling system. Then we have the level crossing, and there's a train protection, which is ETC level 1, which got balances and LEU on the wayside. And the train-borne antenna and train-borne computer is on the train. So that trains, we are not part of this assessment. Then point machines. So these are the main assets in the signaling system we are assessed. They were around 2 to 20 years old. So we had some of the background information of them. So some of them are new actually, just the warranty period is passed. The main issue is that some of the assets were frequently failing and they were operated with workarounds. So they invited us to give them an expert opinion. about what they need to do immediately so that the railway is kept safe. The scope of the project is to perform asset inspection, mainly visual inspection, and provide the score asset condition. There is a scoring matrix that asset good, bad, all this is for the layman's understanding that scoring is based on some criteria. Then we provided some recommendation for immediate attention and for the long-term attentions as well, so that they can implement a systematic improvement program in place. So to start with is the we need to look at what we are to look at. I mean, as I said, it's a national railway. It's around probably 1,000 kilometers. So to do the track walking and visit each of these equipment rooms is not easy for 1,000 kilometers. So we need to prioritize which assets we want to look at. So we looked at the it may not provide the full story of the asset conditions. Just visual inspection, as I said, you will not get it. So you do a failure analysis first so that you understand which assets have been failing. So the LC stand for level crossing. There are several level crossing and point machines have been failing. Interlocking and all were fine, so there was not much of an issue. So we prioritize the assets and we done for all of these assets, which have been prioritized about 25. So we put a criteria 25 to be on the safe side so that we can evaluate fairly accurately. Then we perform the CROAMS analysis to evaluate beta and also the instantaneous MTBF. So as I said, if the bathtub curve, your equipment are not in the flat path, your normal MTBF equations won't work. You have to work on specific distributions. CROAMS have got a specific formula to evaluate MTBF and the failure rates. So that's we have used. Then we perform the causal analysis, whichever the data available. But we also spoke with the maintainers. So you collect the data from various sources, then you infer, OK, this is likely to be the issue, these areas. Then recommendations were derived based on the analysis, visual inspection, and the domain experience. So in this one, because in the webinar, we just look at analysis on done one of these assets, 23P06. The same methodology was repeated for all the other assets as well. So ProAMSA, there is no tool available, so you have to bear with a bit of a maths in this. So it's related to the position of the bathtub, and the model is NT. Is a number of failures. Is a failure of the lambda t raised to beta. Beta is a shape factor, and lambda is a scalar parameter. And I'll just show the practical elements of it without too much going to detail into maths unless essential. So this table is we start with an observation interval. So what we do is that all the number of failures. So for example, in this we have 30 failures. We divide it into intervals and binned the number of failures. And this is quite important for CROAMS. As I said, it's a bit of a macro level analysis. So instead of plotting each failure, we are actually plotting the intervals. So you got 5 intervals and you got 30 failures. So this is to start with. Then there is something called a maximum likelihood estimation. Maximum likelihood estimation. I'll give a bit of a background on it. It's a method of estimating the parameters for an assumed probability distribution, which means that in simple words, we can say that which are the best parameters or coefficient for my model. I have a model, so how I can estimate that? So this model, as I mentioned, is based on the curve from the number of failures and the intervals. So in this, you have 2 parameters. One is the time interval and the number of failures and the beta. So if there is an uncertainty on the beta, you don't know that, and you know the number of intervals is k and the number of failures also. So this function you need to bring it into 0. whichever value of beta which can bring this function to 0, that means that your parameter is correct. I think you only need to worry about that much when you apply it. Maths part, I will leave it to my MSc notes. If someone is interested, I can take it later to revise my MSc notes for that. Okay. So here in the spreadsheet, you have to put together a small model. You have the TI and the beta value. When you trial it, you put a TA raised to beta, and this is a natural logarithm. You multiply the TA raised to beta, and you calculate the MLE sum using this formula. And you use there's in Excel there's a method called goal-seek method. What you do is that you define this function should be 0 for changing the value of beta. So that goal-seek would calculate the correct beta value for it. So then you can use it, and it gives you the results for what is the beta value. And this is the lambda value, which is not the normal lambda you see as a failure rate. It's a scalar parameter. This is calculated by number of failures and maximum of this period. And again, you need beta for this. And once you have that, you can calculate the MTBF using this calculation. MTBF is 1 by, this is not our normal MTBF calculation. It's a special calculation for when the failure rate is not constant. So this is in a nutshell the Crow-Amsa methodology. I don't think the time will allow to explain more than this, but then how we use that I will show there. I mean, for the spreadsheets, it gives a little bit more. You have to do a goodness of fit test here in the chi-square test, and you have you calculate the value, and if that is less than the deviation, then that shows as a test pass. And the interval, you should not have more than 20% in this one of the intervals. These are the two tests to hold the Crow-Amsa distribution is correct. Then you will have the when you plot the logarithm of the operating hours to MTBF, it will be a straight line, and you can see that it is dropping down. That means that the reliability is deteriorating. And there are other usual statistical stuff, 90% confidence interval for the lower and upper. You can calculate using these chi-square values. So this is the spreadsheet for each. So there is a pain to put up this first model, and once the first model is done, you just replicate for each product, each element under analysis. But again, if this doesn't pass, this test doesn't pass, and the integral aggregation is required, then that means that the value you have to take it with a pinch of salt. Otherwise, you can believe. So in this case, you have beta value more than 2. So that means that's a bit worse. So you start to worry about this point machines and all. So then this is the output. Then you have the MTBF. Then you go a little bit more deeper and see what are the failures, what are the main contributors for it. The main contributor, we found that 47% due to mechanical linkage failures, and there are low lubrication issues, if not frequently lubricated. Then you have the backdrive issues, which is the electrical fault itself. And there is a power supply fault also with 30%. So the most top 2 contributors are mechanical linkages and power supply. So if you focus on these 2, lubrication also is part of the overall. If you do it properly, you shouldn't have that. Then the point machine should extend its life further. So that's the value added from this part. This you cannot deduce from a visual inspection, because when you go for a visual inspection, it is overall and kept ready for you. So then you won't be noticing much issues with the mechanical linkages. So we did for a lot of the other point machines also. Then there are some were quite high, 3.37 and also. And we have a scoring metrics for the client. They won't really appreciate telling them about beta factor, instantaneous MTBF and all. So you have to have this is good. So that means that your beta is between 1 and 1.5. Yeah, that's OK. It's more or less in the steady state. You can live with that. Average means that, you need to start becoming a bit nervous about this 1.5 and 2, that you need probably increase maintenance, increase inspection to have less service affecting failures. And 2 to 3 means that you are in the poor condition, and 3 to 4 actually you are quite critical. So this so this is our overall findings. And you can see we have given simple graph on the how we have done the beta value where it exceeds. So the majority of the failures were electrical issues, transformer. Then the lack of failure. In many cases, the failure information was lacking. Then the point machine specific failures, there appear to be random, and because the greater number of failures is not that frequent. Then we recommended for the upgrade, and also for the linkage of the point machine also need to be upgraded for these all the point machines. So the conclusion of the overall exercise is that the visual inspection, it cannot be substituted, but it can be complemented by the reliability analysis. The inspection can be prioritized by the output of the reliability analysis. So you know that the critical and which is good, which is bad. So in a very simple format, you can get that output. Constraints, obviously the failure data, it needs to have a some causal information. So otherwise, also there are ways and means you can collect it. You talk to the people because people have all the information in their head. So you need to extract them. It takes a bit more time. And some of the issues we have found that it is in other systems like system integration issues, because when they bring in new upgrades, say for example, you're running a new rolling stock, then you need to do site integration tests for these at different location and make sure that it's all working okay. Then there are cases where the track layout has changed, but then the data in the system has not been updated. So then that was causing issues. Then they have some manual workaround for this. So all this integration part is quite important. And you should have a robust forecast process in place. And yeah, upgrade of the elements as per the individual analysis. And one particular thing we found in the control system is that software failure. When the software failure happens, the maintainers come, they just come and reset it. And obviously, when you reset it, the software failure goes away. But it is not managed, it's come back again. And what we have found that for the control systems and all, because the software failures are not root cause analyzed, it appears again and again. Resetting is not a solution. It only temporarily removes that current environmental parameters, and that environmental parameters would come back again, and the system is going to fail. So it is quite important when you have the software failures during the warranty period, you should get the supplier to install the data loggers, and that data loggers exactly capture the environmental parameters so that they can replicate that test in the lab. Sorry, the failure in the lab during a test. So then it can be fixed. So this particular project, I think the warranty period has expired and the software failures were not fixed and they were struggling with that. So this is quite important. And failure data, there should be some kind of audit to make sure that the data is completeness of the data in the ERP system. Because if you do not have the failure data, you won't be able to improve yourself. If there is an issue and if you are not reported it correctly, then even the experts cannot help you on this. I just utilize this opportunity for the Intellects training courses. So we have the specific discipline courses. This is mainly for the system safety, RAM engineering, system engineering, assurance. This is on an online portal. It is with recorded lectures and the animated with animations and all. So you would be able to understand from the narrative and also with the notes, and we are supplementing this with the contact sessions also. So if you want to improve your knowledge in system safety, RAM engineering, system engineering for each individual, this would be quite helpful. And this is a skill which is in demand in railways. And we have a bit more professional certificate courses, which is a amalgamation of these modules. Plus, there will be exams and there will be more the coursework depending upon which certificate course you do. This one railway ramps certificate. This will have the contact sessions and there will be an exam as well. And once you pass, you get a CPD certificate. Then the system engineering ramps, it's around 56 hours of CPD. This have a coursework instead of an exam. Then advanced certificate course is system engineering And after that, there is a case study for 1 week. This is done through live sessions. So we'll be working on a real-time project, conducting the HAZOP sessions, preparing the safety case. Some elements of these things we cover it in 1 week, so that you would be able to start as a basic practitioner in these areas. And the appreciation course, this is a 2 days live session. This is mainly who wants to have an appreciation of this without going to detail. This covers more on the breadth than depth. So they conduct only for group training, and it's live sessions through Teams. And the EMC overview course, this is a 4-hour CPD. This is a comprehensive overview course for the EMC. It is done by Mr. Stuart Charles. So he'll be doing a webinar next week as well. It's clear. And we are also launching a new course in the EMC application of railways. This is in 3 4-hour sessions, group training. This will also include the practical demonstration and how it's applied to the railways. It's a very interesting course. Stuart will cover this aspect in the next webinar as well. And we do customizable courses if you want to do for as a group and you want specific requirements. So if you are covering those topics, then we'll be able to do that course for you. This is the next webinar Stuart providing next week, same time. And this is on the EMC on the railway. So he provides examples of EMC phenomena with a short introduction of a EMC demonstrator. It's a cable crosstalk. So this is part of the new course as well in detail. So he'll give a glimpse of those topics as well. Okay. So. Okay, that's on. I think I just slightly exceeded the time. So if you have any questions, yeah, I'll try to answer them. You have followed.
Hi, Rishi, it's Raj here.
Yeah, hi, Raj. Yeah.
How did you identify that electrical failure? That I did not get it. That like electrical and mechanical. You said you have done the assessment instead of site supervision or the inspection.
We do functional tests at site. So then I'll go to that checklist here. So when you're doing that inspection, so we do a functional test on the point machine. So we open the cover. As we see, this is one of the photographs from that project actually. And we do the functional test and we see whether the temperature is more, and we check the current consumption if it is too much, and if there is a delay in throwing the arm. So those are the kind of things you need to know a bit about the domain to test that.
I think I missed that, but I think I might have just jumped. Okay, thank you for that.
Yeah, no problem. Yeah. Any other questions? I'll also show you the portal, what we are actually our training portal, which has all the courses here. So let me just share the system sound also so that you can see. So this is our training portal, which shows all the types of courses we have, and certificate course, advanced course. Then this is the certificate course in system engineering and all, and we got tests as well here. Then we had the live sessions also, which is recorded and will be available in the portal, so that you can always refer back. And we did specific course for some of the clients, like functional safety course. They were doing product development, so we were doing that as well. So if you go to the one of the thing, for example. So
times 84 times 10 to the minus. In order to do, we can. So whatever the architecture we use to achieve our cell target, we must first determine what the appropriate cell level is to be.
Yeah.
IEC 61508 is an international standard describing methods on how to apply, design, deploy, and maintain automatic protection systems.
It gives a background
related
systems. About the cell, then it goes to the quantitative measures. What are the?
There are two basic ways of
that here, and it's a narrative, and you also have all the narratives in the notes as well. So you can always refer back and
the CAS organization provides guidance on demonstrating compliance with.
So then we have an example as well here.
Now let us take a look at how we can determine a safety integrity level requirement. In this example, we're going to consider a level crossing controller. There is a top-level safety objective stated for automated level crossings. To expose the individual occupants of road vehicles to a risk of fatality.
Problem. Then what are the assumptions you can do? And because once you cover this theory, this is the practical example where you will encounter this kind of
when a car crosses. This would follow on from a collision between a car.
It gives a
let's have a
calculation. This is first you demonstrate. This is the
calculation.
Safety
how you
is good do practice, the tolerable hazard.
But at the end of the day, you always need to consider practicality and cost.
How you apportion to the tolerable
for 10,000 kilometers.
So that
is
each
the probability of
component
it being safe for one to the.
So this particular component
now
we calculate and we come up with the TFFR
finally,
level.
We divide this by the total number of hours per year, that is to say HPY, to get the hourly value. And we find that TFFR-H is less than 5 times 10 to the minus 9 per hour. To achieve this, we need a SIL4 value.
It's as you can see, these are quite comprehensive material. This is the live portal. Some of you may have already gone through this. So, I mean, this is just on cylinder. There are 31 slides, which that's why it takes 18 hours. You need to spend time, but then it is well worth the time, I would say. Okay, I won't go through that too much. Then. So any other questions on this?